Welcome, students. Have you ever really thought about how all the lights in a room can be on at the same time and they're all equally bright? Well, it all boils down to one of the most important ideas in electronics, voltage in a parallel circuit. In this explainer, we're going to demystify this whole concept. By the end, you'll be able to look at pretty much any circuit diagram, no matter how messy it looks, and know exactly what's going on with the voltage. All right, let's just jump right in with a little puzzle. Take a look at these two circuits. On the surface, they couldn't look more different, right? One is this nice, clean rectangle, and the other one's kind of all over the place. But here's the big question. Are they electrically the same thing? We're going to find out. So to answer that question, we have to get on the same page. We need to go back to square one and lock down the official definition of what a parallel circuit actually is. You know, getting this one definition right is the key to unlocking everything else. So what is a parallel circuit? The best way to think about it is like a river that splits into a bunch of smaller streams. Now, each stream is its own path for the water, but, and this is the important part, they all start at the exact same point, and they all meet back up at the same point downstream. In a circuit, our components, like resistors, are the streams. Each one gets its own path, but they share the same two connection points. Now, let's talk about those connection points, or nodes. It's really easy to just see a little dot on a diagram and think, okay, that's the node. But it's more than that. A node is any continuous piece of wire. Think of it this way. If you can trace a path along a wire with your finger without jumping over a component like a resistor, you're still on the same node. The whole wire is one node. Let's see that in action right here. See that top wire? Electrically speaking, that entire wire is one single point. We'll call it node A. And the entire bottom wire? You got it, that's node B. Now look at those resistors. Every single one has one leg connected somewhere on node A, and the other leg connected somewhere on node B. And that, right there, is the textbook definition of a parallel circuit. Okay, I get it. Circuit diagrams can be messy. Sometimes they're even drawn to be confusing on purpose, especially on exams. But don't worry, I'm going to give you a really simple mental model that will help you cut through the confusion every single time. This is hands down my favorite part. We're going to simplify this whole idea down to something we all know, a simple ladder. Seriously, this analogy is an absolute game changer. Once you see it this way, you'll never be confused by a parallel circuit again. So here's how it works. The two long vertical rails of the ladder, those are our two nodes, node A and node B. And the resistors? They're like the rungs of the ladder that you climb on. Now, think about a real ladder. The distance between the two rails is the same on the bottom rung as it is on the top rung, right? It's constant. Well, voltage is just like that. The voltage distance between the two nodes is the exact same for every single resistor. And that ladder analogy perfectly illustrates what we can call the single wire theory. In the world of circuit analysis, we just don't care how long a wire is or how many bends and twists it has. If points are connected by just a wire, they are, for all practical purposes, the exact same electrical point. They're all part of the same rail on our ladder. All right, enough with the theory and the analogies. Let's get our hands dirty, so to speak. It's time to move from the diagrams on the page to the lab bench, because seeing this stuff work in the real world is where it all clicks. Okay, if you only remember one thing from this entire explainer, I want it to be this. This is the golden rule. In a parallel circuit, the voltage is the same across every single branch. I'm going to say that one more time because it is that critical. The voltage is the same everywhere. Burn that into your brain. And here's the proof in the pudding. We've got a circuit on a breadboard here. Our power supply is set to 12 volts, and we have 3 resistors hooked up in parallel. Now just look at the voltmeters. The one on the source reads 12 volts. The one across the first resistor, 12 volts. The second, 12 volts. The third, you guessed it, 12 volts. The rule holds true. This is how we bridge the gap between the real world and the world of diagrams. The physical circuit on the left, that becomes the neat schematic on the right. Sure, the wires and resistors look a bit different, but the electrical logic, the truth of the circuit, is exactly the same. The source voltage is equal to the voltage across R1, which is equal to the voltage across R2, and so on. So, now that you're armed with this fundamental rule, let's put it to the test with a classic problem you might see on an exam. I'm also going to show you a very common trap that trips up a lot of students so you can spot it a mile away. Okay, here's our scenario. We've got a 25-volt source, and it's connected to 5 resistors, all in parallel. But here's the little twist. They all have different resistance values. We've got everything from 1 kilo ohm all the way up to 3.3 kilo ohms. This is where people start to get confused. It seems kinda intuitive, doesn't it? A bigger resistor is a bigger obstacle, so it must take more voltage to push current through it, right? So is it true? Does that bigger resistor see more voltage? The answer is a definite no. Remember our golden rule? If the components are in parallel, the voltage must be the same. The resistance value has zero effect on the voltage across it. What it does affect is the current that flows through it thanks to Ohm's law. But the voltage, every single one of these resistors sees the full 25 volts from the source. And now for the trick I was telling you about. I call this the geometry trap. Professors and textbook authors love to draw circuits like this. They make it look like some kind of weird triangular mess just to fool your eyes. But we're not going to fall for it. Don't let the weird sheep distract you. We're going to use our secret weapon to find the truth here. We're just going to trace the nodes. Okay, let's do this together. Start at the top of the battery and trace that wire with your finger. It connects to the top of R1, and it keeps going and connects to the top of R2. See? That's all just one node. Now let's do the bottom wire. It goes to the bottom of R1 and continues right on over to the bottom of R2. That's our second node. So what does that mean? It means that even with this tricky drawing, both resistors are connected to the same two nodes. And if that's true, they are in parallel. So if the source is 50 volts, what will the voltmeters read? They both have to read the full 50 volts. We've beaten the geometry trap. Okay, let's wrap this up by quickly recapping the key takeaways from today. These are the absolute non-negotiables you have to remember. Here they are, your 3 essential rules. First, the rule. Voltage is identical across all parallel branches, period. Second, the geometry. Ignore how it's drawn, trace the nodes, and think like a ladder. And third, the independence. In a parallel circuit, changing a resistor's value changes its current, not its voltage. And I'll leave you with one final challenge, just to make sure this is locked in. Look at this circuit. If we were to increase the resistance of R1, what would happen to the voltage reading across R2? Take a second and think about it. If you've been following along, you already know the answer. Thanks for watching and happy circuit building. You know, one of the toughest jumps in any circuits course is going from those nice, clean schematics to the messy reality of a breadboard. And it's a skill that's not just about crunching numbers, it's really about recognizing patterns. So today, we're going to become circuit detectives. We're going to learn how to spot the electrical truth that's hiding right under the physical layout of our circuits. All right, let's get into it. So here's our game plan. First, we'll nail down the basic rules for identifying a parallel circuit. Then, we'll take those rules and apply them to a real breadboard. After that, we're leveling up to a professional circuit board. We'll figure out why this all matters by looking at the electrical consequences, and I'll wrap it all up with a simple checklist you can take right to the lab. All right, first things first, before we can go out and spot these circuits in the wild, we've got to get the basic rules down. The lingo, the core ideas. This is where we build our foundation. So let's start with a really simple idea, the branch. I want you to think of current like water flowing through a bunch of pipes. When that main big pipe splits off into smaller ones, each of those new paths is what we call a branch. It's just a different road for the current to take. And this right here, this visualizes it perfectly. You see that total current, IT, coming from the source. The moment it hits that first intersection, it splits up. A piece of it, I1, goes one way, and the rest, I2, goes the other. That splitting of the current, that's the dead giveaway, the absolute signature of a parallel connection. Okay, next up is the node. And I gotta tell you, this one is huge. See, on a diagram, we just draw a little dot. But in the real world, a node isn't just a dot on a page. Think of it as an entire region of connection, a wire, a trace, anything conductive, a whole area where the voltage is exactly the same everywhere. And this slide? It just nails the concept. Look at that blue highlighted wire up top. Every single spot along that wire is electrically the same place. It's all just one thing, node A. Same goes for the green wire on the bottom. That's all node B. It doesn't matter if the wire is long, short, or squiggly. So get this in your head. A node is a region, not a dot. That's the key. And all this leads us to what I call the golden rule of identification. This is the single most important thing you'll hear today. The physical shape, the geometry, it can totally fool you. What actually defines the circuit is how things are connected, its topology. Your job as a circuit detective is to look right past how it's laid out and see how it's actually connected. And bam, here's the golden rule in action. You've got 5 circuits here that look completely different. One's a ladder, one's a box, they're all over the place. But go ahead, trace them out with your finger. In every single one side of every resistor goes to node A, and the other side goes to node B. The drawings look totally different, but electrically, they are one and the same. Okay, that's enough theory. Let's get our hands dirty, well, virtually, and see how this actually works on a breadboard. We're taking it from the page to a real prototype. So, here's where the magic happens, right? The translation. On the left, you've got our perfect little schematic with node A and node B. But on the right, that's the real world. That abstract idea of node A is now a physical thing, that entire top row on the breadboard. We're literally building the node with our own hands. So how does that even work? Well, if you could peel back that plastic, you'd see that those power rails are just single strips of metal connecting all the holes in that line. So when you plug your resistors into that top rail, you're literally forcing them all to connect to the same point. You do the same thing for the bottom rail, and just like that, you've built a parallel circuit. Pretty cool, right? All right, Professor's Challenge time. This is something you're going to run into, I promise. You're building your circuit, but your parts are spread out. How in the world do you connect R1 to R3 when they're on opposite sides of the board? And the answer, my friends, is the humble jumper wire. But here's the thing. Don't just see it as a piece of wire. You got to see it for what it really is, a node extender. That little wire is physically stretching node A across the board, making sure that everything connected to it is part of the same electrical family. Okay, awesome. We've got the breadboard down. Now it's time to level up. Let's tackle a professional printed circuit board. The rules haven't changed, but this time the clues are etched in copper. So on a PCB, you can forget about those jumper wires. Here, the connections are permanent copper paths called traces. The layout is locked in. So our job as a detective is to become a trace follower, hunting for those nodes and figuring out what's connected to what. Okay, let's look at this upper section of resistors first. Just follow it with your eye. See that big, wide copper trace coming off pin 1? That's our first node. Now look at the trace coming from pin 2. That's our second node. Now look at all those resistors, R1 through R4, R11, and R12. Every single one is connected between those exact same 2 traces. Case closed. That is a textbook parallel setup. Now check out this second group. This is where you really have to put on your detective hat. Now it's easy to look at R9 and R10 and think they're doing something different, right? They're kind of pushed off to the side. But if you follow those skinny little traces, they snake right back to the same main traces that R5 through R8 are connected to. See? The geometry's just trying to trick you. Always, always remember that golden rule. Connectivity is everything. So you might be thinking, okay, great, we can spot these parallel circuits. So what? Why does this even matter? Well, it matters because this particular arrangement has a massive, predictable impact on how the circuit behaves. It's all about the electrical consequence. Well, this is the payoff. This is the whole point. Because every single one of those components is wired up to the exact same 2 nodes, they absolutely must have the same voltage across them. It's a law of physics. So if your power source is pushing 5 volts between node A and node B, then every single one of those resistors gets the full 5 volts, no exceptions. And that fact is the key to analyzing these circuits. All right, to pull this all together, let's create a simple checklist, something you can actually use every single time you look at a new circuit. Here it is, the detective's checklist. 4 simple steps. First, identify your nodes. Find those common areas of connection. Second, and this is a big one, ignore the geometry. Just pretend it doesn't matter where things are placed. Third, trace the path. If the current splits up and then comes back together at another node, you've found a parallel circuit. And finally, step 4, verify it. Don't just trust your eyes. Grab a voltmeter. If they're really in parallel, you'll measure the exact same voltage across every single one. So there you have it. You now have the toolkit to look at a messy board and see the clean, simple topology hidden inside. So I'll leave you with a question to chew on. We now know that in a parallel circuit, the current splits. So, what do you think is the one key thing you'd look for to identify a series circuit? What does the current do there?